Right, I'll just start this then, considering there's probably only one person watching, but the first time I've done this, so I'll just jump right in. So this is what I've been working on the last, well, I did this a while ago, but I've come back to it and going to try and kind of just kind of break it down and run through how I got to this stage. It's still a bit Ruby, like if you look up here you can see the texture repeating. That's mostly just the texture map repeating. The actual waves themselves, you can kind of see some waves repeating if you look in certain angles, but for the most part I'm kind of happy at this stage. So let's go to how I found out about this. Just going to open up this page. So this is the Nvidia GPU gems. GPU gems paper, and it kind of goes over some of the maths and how these things work. It's basically just a kind of a cheap way of getting realistic waves. It's kind of physically based, not properly physically based, but we'll just kind of go through it one by one. Now, I'll start with a blank scene, and we'll just go through the paper and build it up step by step. So let's go to new level. I'm going to create a default level. Save the existing one, and I'll delete this thing. So I've got this grid here, which I'm going to use as my base, and I'm just going to scale this up. There we go. And the wireframe for this looks like that. So we're going to be displacing this thing. If you're doing just world position offset in the material, so if you're just moving the vertices, then your resolution of your grid is going to matter. And I'm going to use some tessellation here though to kind of upraise this, but we can just test this on the low res grid. So this is the material at the moment, but the actual wave itself is this thing. So this is what I'll be building first, and then I'll kind of show how you can package it up and build a more complex wave. So let's close this. There we go. And go back to the paper. So the main thing this does, let me just scale this up, is it talks about how first you can sum some sine waves. So if you don't know what a sine wave is, I can just start from there and show you that. Let's create a new material. I'm going to call this Gerstner wave tut, and just open this up. And I'm just going to give this a color just so we can apply it to our mesh and see something. And I'll make this blue, so because all oceans are blue, right? There we go. And sorry, I'll probably forget to bring this across, so if you're in the chat, let me know, and I'll make sure I'm showing the right thing. So let me just drag this onto our grid so we've got something. There we go, it's got a nice blue grid. So first I'll just show you what we can do with world position offset, and then later on I'll go into the tessellation. So sine wave, if I just do a sine wave, this takes an input, and this input kind of goes from 0 to, I don't know, whatever, infinity, and then the output is going to be the height at that position in the wave. So we can say input time. So we can input time, and then now if we plug this into world position offset, which has to be a vector, and we want to push this vertically, so we're going to make a vector, make float 3, and then we're going to push it up, and in Unreal, up is Z, which is really annoying if you're coming from Maya. So I'm just going to hold the 1 key and press down, and you get this nice little constant. So make 0 for these two. So we're not going to move the vertices left or right, but we're going to use the sign. So we're going to push it up and down. So this is going to be our world displacement. And what we'll get now is we should hopefully see it moving up and down. One thing is hard to see is like how much it's going up and down. So it's probably good to kind of put in some assets so you can kind of see how much it's moving, have some kind of visual scale reference. So let's choose a tree or something. Oh, these are from the kite demo, so they're probably quite hardcore in terms of triangle count, but let's just try dragging in some branches or something, that might help. Sometimes these take a while to load in because the triangle count is crazy, but we'll give it a go. Come on, any second now. It's just dragging in a mesh, how slow can it be? Any second now. I mean, I've got 64 gigs of RAM and I've got a GTX 1080, so come on. Spinning box, spinning box. Come on. There we go. Great, so we've got this thing, so now we can kind of see some kind of visual reference. Now you can also see the thing going up and down, so that's the sine wave going up and down with time. So we probably want some kind of control to multiply how big this is. So let's just hold down the M key and going to multiply this by some value. I'll convert this to a parameter, and I'll just call this call this amplitude. So it's just a gain. And I'm going to go to 5. Compile this. So this will be going up and down like that. So you can see it pulsating, and if we want to change the rate that that's pulsating, we can change the input to sine. So if we multiply time now, that will change the speed of this input, because time is that input. So we can multiply time by 0.5. I'll make this a parameter as well. I like to make a lot of things parameters, then I can just drag and see the effect of them as they happen. So let's call this time mult and drag that into the input. So now when we scale this down, I'm very sorry, I keep forgetting to do that. So I've got time being multiplied by this parameter, and we can change the speed of the input now. So if I drag that down to say 0.1, then the rate of this sine is going to be a lot slower. And then we've got that going into this multiply, which is the amplitude. So that's like the most basic kind of way you can use sine to go up and down. Now at the moment we've only got time as our input. We want to use position now as our input. So if we go back to our paper, what it's doing is this is going to be our simple sine wave. So this is the equation for a single sine wave, and I'll go through all these parameters soon. But I'll just show you kind of the principle of it is, so instead of using just time as an input, we can use position. So I'll disconnect time now, because that was giving us the vertical up and down. Let's use position. So we can just use world position, and it should be here. So this is going to be world position, and let's just use the x position for now. So as the vertices are increasing in x, we can use a mask for that. We'll just take that off. As they're increasing in x, that's going to drive our sine wave value. So we'll get that out of the way. So we should see a static thing here. So let's scale this up like that. There we go. So it's easier to see if we have a wireframe. Oh no, it won't do it in wireframe because world position doesn't work in wireframe. Let me make this a bit darker so we can see. I'm just making my color darker so I can see this thing. We're also not changing the normals yet, so it's harder to see. So let's change my light position so we can. There we go. So that's easier to see now. So we're getting this this sine wave thing. Let's make this smaller so that the resolution is better. So we're using world position here as a input to the sine wave. So it should technically stay the same shape as we change that, but I think because I know why this is happening, the resolution of the grid is kind of misleading us here. Let's go to wireframe. So this is the resolution of the grid, so it can only ever kind of really change at this rate. The actual input to sine, in world position, these units are changing quite rapid. So in reality, this is going up and down, up and down, up and down, because we're in centimeters. So what we need to do is scale this down so that our changing units happens over a larger space of time. So we can just do that with another multiplier. So this is similar to doing this multiply against time. Instead of that, we're going to do a multiply against space. So we'll do constant, so we can just hold 1, drop that down. We'll convert this to a parameter, and I'll just make it 0.01 or something. And I'm going to call this space mult, and then drag that into that. So now we should see, if if we just keep scaling this down, we should get something more what we want. There we go. So that's what I'm after, is as x is changing, and you can see it's x because we've got our little gizmo down the bottom here. As x is changing, that's our input. The x value of the vertices input into sine. And then we can change the size with this one, with the amplitude. There we go. So now we've got like a static input. So what we want also now is, if we add to this position, if we just simply add an amount, that's going to be an offset. So we can, let's just do a quick adding, and another constant, and convert to a parameter, and let's call this x offset, and it doesn't have to be anything yet, but we can do, let's add it here after our space mult. So we're going to get our x position that we've multed down, and then we're going to add to it, and that's our input into sine. And then as we add to this value, it's basically changing what x value is going into sine. So we're going to get a different value of the sine wave. So instead of making this increase, what we could do is use our time input, and that's going to just take place of our offset. And if you guys have any questions, please just put them in the chat and I'll try and answer them. There we go, we've got like the most simple sine wave ever. The main problem with this though is that, one, it's a simple sine wave and it looks pretty horrendous, but the other thing is it's only ever going to go in the x direction because we're taking the x value of the vertice. So we could change it to be the y, the y value, because I'm in Unreal. So that will now make it go in the other direction. There we go. So if we wanted to make this going any kind of arbitrary direction, we kind of need to way to take the x and the y values and modify them so that they kind of go some proportion in x and some proportion in y. So let's kind of have a look at the paper and see what this is doing. We've got, I suppose we can just dive into this and kind of see what it does. So here we have time, t is time. This thing here is a phase constant, which is basically a multiplier on time, which is kind of what we had. It defines it as a speed parameter, which we kind of input, which is like our multiplier, and it also does it by 2 pi over wavelength. So we're gonna be defining this thing called a wavelength, which is like how far apart these crests are. So you can kind of see, let me change that back to x. You can kind of see these peaks here, they're a certain distance apart, which we could measure. But we want to kind of explicitly tell the system how large that distance is, and we can do that with this equation. So we also have our amplitude, which we kind of already put in, which is just kind of a scaling on the height, and speed, which is going to be our custom parameter, and direction, which is going to be, in this case, a 2D vector from top down. So we're going to be able to define a 2D vector, and that's going to kind of interact with our x and y parameters. So let me just kind of go here. So the way this works is we have a direction, and this is our 2D vector, and we're doing a dot product with the x and y position. So let's do that first. So if you don't know what a dot product is, I'll quickly go over that. It's easier to show on a sphere here. So I'm just going to take off this whole position, and I'm going to get my camera vector. Here we go, camera vector, and my surface normal. because this is going to show this visually, so I'm just going to get my normal, vertex normal in Unreal, so vertex normal world space. So I can do a dot product on both of these things. So this is a mathematical operation. I'm not going to show you how to do a dot product. I'm just going to show you what it does. Let's do a dot product, and let's hook this into the base color, and we'll hit OK. Maybe this isn't the best example of it. Maybe we want I vector, is that what it's called? No, camera vector. Camera direction vector. Maybe that's what we want. Okay, so dot, maybe this needs to be normalized. Let's normalize these and make these a length of 1. And I'll get my vertex normal. And maybe this needs to be reversed. So let's multiply this by -1. And yeah, I'll put the video up on YouTube after this. So let's try that with -1. We'll do that, and we'll do other vertex normal. This might be what we want. Yeah, that's kind of what we want. So the reason this wasn't working was because the camera vector is going from the camera to the object, whereas what I want is the pixel to the camera. So let's get paint out, because that's really helpful. So I'm just going to do some drawing. So let's say we've got our sphere, and we've got our camera coming in here. So this is our eye, like that. So what a dot product does is it takes any two vectors. So let's say we've got our normal here, and we've got our camera vector here pointing out this way, but towards the camera. So ignore the fact that I've drawn those two there. So the angle between these two things, the dot product can effectively take this angle and give us back a single value, which is between 0 and 1. That's kind of assuming that these are normalized. These are the length of 1. So if this has a length of 1 and this has a length of 1, then the value it gives back is going to be between 0 and 1, and actually between -1 and 1. Because what it can do is, if the angle between these is 90 degrees, then the dot product is going to give you 0. And if they're both pointing in the same direction, so if the surface normal is pointing directly at the camera, so if these are exactly parallel, then you're going to get a value of 1. And if they're pointing away from each other, so if the vector to the camera and the vector here is pointing away, so the back facing, you get a value of -1. So it's a really kind of easy way to get some kind of mask. And you kind of see, it's quite hard to see here, but it is white here at the edges. I think there's some kind of tone mapping going on here. If I made this a unlit material, let's make it unlit, and plug this into the emissive, then we should see That's really strange. Yeah, you can kind of see it. It's kind of black at the edges. There's some kind of weird tone mapping going on here, but I'll just ignore that. And I'll put it back to default lit. There we go. And we want our inverted one. There we go. So that's what a dot product does. And we can use that now. So going back to what we're actually trying to do is we can use that dot product with the X position and the Y position to give us a kind of a mix between like that X wave and that Y wave. So let's kind of just hook that up. Let's get rid of our vectors here. You'll see what, in a second what's going to happen. So let's get our X position, which is this thing here. So we've got our world position, and we're going to, well, we don't need the single one now because the dot product is going to do this for us. We're going to take the X and Y. So we've got a 2D vector, and we need some kind of input direction. So we're just going to use a color for that. And this is going to be pointing like in X and Y. So we want some proportion of red and some proportion of green. For some reason it decided to just freeze because it does that sometimes. There we go. So let's just say we want 0.4 in red and 0.6 in green. So let's do that. So we're going to normalize that because this might not necessarily be a length of 1, but we want it to be normalized, because if you normalize two vectors, if you dot product two normalized vectors, the value is going to be between 0 and 1. It just really makes it really easy. But actually, in this case, I'm kind of getting ahead of myself. We don't want to do that because we want it to be kind of scaled. So what I explained about the whole between 0 and 1, that's really useful for masks and kind of Fresnel type effects. But in this case, we don't want to do that normalization. I'm kind of ignore that part about what I said, because we still want that scaling in X and Y, but it's going to give us what we want in terms of mixing between X and Y. It's hard to explain, but you'll see it visually when it happens. So I don't want to normalize it, but I do want to dot product this against a 2D vector. So let's get this. So we have a position here, and I'll comment these now. So let's just go 2D position, 2D X, Y position, and this is going to be our direction vector. So let's comment that. Hit the C key, comment. There we go. And let's dot product these two now. So we go into input A and into input B. I'm not sure what this is going to look like here, but we should see something increasing in X and increasing in Y. There we go. So what this does is effectively is giving us a ramp from in a certain direction, which means now we can change our so it's instead of increasing in just X or just Y, what it's going to do is increase in the direction that we specify. So let's get that color, and now we can change that ratio. If I drag just around here, hit OK. Actually, it makes sense if this is a parameter, and I'll call this direction, because then we can change it in the viewport. Just hit apply. There we go. So now, as we change this round, you can kind of see it should change in the viewport. There we go. Bit slow to update. So the dot product basically is giving us a mix between X and Y. So when our wave is, when our direction is going in X, then that's gonna kind of dot product against the X component. So this is our mesh. So we get our verts. So these two dot product together, the world position and the direction vector. So if our direction vector is 1 in x and 0 in y, if that's our direction vector, then we're just going to get back out our x component. And if we have 1 in y and then 0 in x, we're just going to get back out our y component from our mesh. If we have, if our wind is kind of going like that, so it's 0.5 in x and y, we're going to get a mixture of x and y exactly, so it's going to go diagonal. So if I set this to 0.5, 0.5, you see it's going perfectly diagonal for top down. And then if I have like 0.1 and then 0.9, 1x and then 0.9 in y, then it's kind of going to go at a bit of an angle. So 0.1 in x and 0.9 in y. It's a bit hard to see that, but it is. It's at an angle. Let's go like that. Yeah, you can see it's a slight angle. Probably easier to see if I go 0.3, 0.7. There you go. So this direction could be normalized. Just don't normalize your position, because that needs to be increasing. If we normalize the position, then that doesn't really do what we want. So you can normalize your direction if you want. Where's my normalize? Where's it gone? There we go. So you can normalize that if you want. Doesn't really make a difference. It would actually make a difference because it would give us a bit of a scaling. If our wind's direction was stronger, then it would actually make it kind of, it would scale these values in that direction, but that's fine. So now we can use that as our input to our sine. So let's just look at our equation, which is on the paper. So we've got dot product against x and y. So let's ignore this bit, and let's just put that into sine, and that's going to be our final position. This w x y t simply just means we can read it as our final height value at the position x and y is at time t is going to be specified by this. So let's just look at this dot product section being signed. So we're going to get our dot product. Let's just move this stuff out of the way. There's our sine. So we've got our dot product into our sine, and that's going to go, I won't do the amplitude for now, I'll just do the straight sine. And if we move that out of the way, then let's see if we can see this. Probably can't because it's needs to put this color in. Oh, I mean, it didn't even plug in our height. So let's put our color back in, and we should see this motion going in that direction. But we won't see anything because it's not very high. So we'll put back our amplitude so we can boost it up. So now we've got our wind direction controlling this sine wave. So we've got our dot product going into our sine, then it's being multiplied up, and that's just going into our make float 3 to push it. So now what we could do is we could change our wind direction. So we can just do that. And now when we change our wind direction, that changes our wave direction, because that's what's driving the dot product. And in terms of our amplitude, then we can just check this, and we can just see this is our amplitude. We're just doing a times sine of this thing here, which is what we've got. We've got, make this big. We've got amplitude times sine of our dot product between these two things. Now let's go back to the paper. So the next thing we've got is we've got this. So we're going to multiply our dot product result. So this is our dot product. So that's what the dot means. We're going to multiply it by this w parameter times w parameter plus t times phase constant. So in terms of order of operations, you always do multiplication before addition. So these are going to get multiplied together, then this is all going to get multiplied together, and then they're going to add. So the adding is what's doing our offset, which is what we saw before. So let's do our W parameter. So this is a bit of a weird one because this is going to involve pi, and that's going to be our kind of starting to get into kind of physical values of frequency. So we actually have this W parameter, which is going to take our is going to be the result of our L input. So it says wavelength L, and that's going to be what we input as an artist, but then that's going to create this W value for us, which we're going to put in here. So let's create this W parameter. Well, first we need to create the L input. So let's okay, so I'm just going to move this time stuff out of the way because we're going to come back to this. This is what we're going to use. So let's create this L parameter. So I'm just going to create a constant, convert it to a parameter, and this is going to be called our wavelength. And let's just kind of underscore L. Oops. Wavelength. Let's just call it L. There we go. So this is going to be our wavelength in actual meters. So we want a default value. Now, considering we're in Unreal, we're dealing with centimeters as our unit. So let's go to 100 centimeters, which is 1 meter. So we need to create a W. So let's go back to the paper. And bring it over here. And we need to create this W parameter, which we know is 2 pi over L. So we need to do, let's just create a constant. This is going to be 2, and we need pi. So I think Unreal gives that for us. So we've got pi, yep. So 2 pi, and it gives us a multiplier as an input. We could do a multiplier node if we wanted to, but we might as well just plug it in there because it does it for us. 2 pi divided by L. So let's do divide. So 2 pi divided by L. So the output of this is going to be our W parameter, which is going to be this thing. So W equals 2 pi over L. And this is the thing that we're inputting, this L thing. So let's comment this, and we'll call this W. And let's just kind of hook it up as to what this does. So we got dot product, the result of that, which is a scalar value, because we're putting in 2 vectors, but we're getting a scalar value out. And then we're multiplying that by our kind of pi value. So let's sorry, I'm completely talking wrong there. Multiplying it by a dot product value. So let's do a multiply, and we'll just get our dot product result and multiply that by W. So this is going to be this part here. So let's just hook that in to see what we get, because we should now be able to look at this and what's going on here. So I think what's happening. Alright, so we did our own multiplying of position here. So let's keep that like that. And then we'll change our wavelength. Okay, so we're having to scale this quite high. Cool, so this is in centimeters. So yeah, our wavelength now is, let's try 3200. That's going to be 3.2 meters, which according to this log thing here, that probably looks about right. Now I wish I had some kind of unit measurement thing here. What have I got my grid set to? Edit, editor preferences. If anyone knows where this grid options are, that'd be great. Maybe it's under project settings, who knows? General settings, let's just search for grid. Oops. Grid, no. Grid, no. under here, set the position grid snap value. Well, anyway, you have to just trust me that this is 3.2 meter wavelength. So let's go to back to our paper and see where we are. So now we need to add time times this phase constant. So this phase constant is defined as a speed parameter times 2 pi over L. So it's kind of similar to this thing where we're inputting this L thing and we're also inputting a speed value, and that's going to give us this phase constant. So let's go back to our material. So we're going to input speed, so we need another parameter for that. So this is going to be called speed. It needs to be a parameter, speed, and let's make it a speed of 100, because that's going to be 1 meter per second, I'm guessing. So let's do, because I have a very bad short-term memory, speed times 2 pi over L. So we've got this 2 pi thing again. Let's just use that. So that's speed times 2 pi over L. Let's just do that. Speed times 2 pi over L. Actually, we want this whole thing. So speed is 2 pi over, that's 2 pi over L, because we've defined it before. We've got 2 pi over L, which is our W. It'd be really nice if it just said S times W. That'd be a lot easier. So we don't even need this. We can just do speed times W. There we go. And let's just kind of comment this and go speed times let's just say 2 pi over L, in brackets put speed times W. There we go. So let's just see what we're going to do with this. We've got a phase constant times time. So we've got time. Here it is. And we don't need to do that. And we don't need a time mult because this is we have our multiplier, which is going to be our speed. So let's just do that. And then it's going to get added. So we've got our t times phase constant, because that's just this thing. So we've got, let's just comment this. So we've got t times phase constant. And let's do add it to this thing. So we've got our, that's the result thing there. So that's this part. So W times the dot product. So that's this part. W times the dot product. And then all we need to do is, let's just move this a bit. Actually, I'll move this back. Add it. So let's just do an add like that. And now we've added them together. So that's the whole thing. We've got that plus that. And that's just going to go into our sign. That's the argument to our sign. So let's do that. Hit apply. Now what I'm hoping to see here is some moving waves. There we go. So this is the most simple moving wave you could ever imagine. Go to our light source. I'll leave that alone. I was going to turn off static lighting, but it should be fine. So this is a moving wave. So now we can come in and start changing things like speed. Let's go to speed and make it faster. So now we've got a faster moving wave that's moving 3 meters per second. 1, 2, 3. Yeah, that's about right. And then we can change our wavelength, so we can make the distance between these crests larger. Now, I believe there's some kind of way of relating these two, some physical way to relate them, which is based on gravity, but I've left them separate for now because I think it's good to have a bit of artistic control. And if anyone's listening, I think I've got 7 viewers apparently, so that's kind of cool. If the audio's okay, let me know, or if there's anything else you want to kind of want me to bring up, then just stick it in the chat. So let's we've got our simple sine wave. Now let's go back to our paper, and what it does is it says the total surface is h xyt, which you can read this as meaning the final height of your vertices x and y position at time t, is the sum of multiple sine waves where each sine wave is kind of given an index. So this just means do a few of them with different directions, and you're varying these things. I mean, it says it over about, where does it mention I? It says to provide variation, we'll randomly generate these waves within constraints. It says it fades them in and out, but basically it just means over all of these waves I, like basically add them together. That's what the sum means. So let's do that. Let's add a couple together. So we're gonna. Now, should I wrap this up in a material function? I probably should. Let's create a new material function. Let's go to here. Go to materials, new material function, and call this simple sine. There we go. Open that up. So our output's going to be pretty much just the output of the sine. So let's well, actually they can each wave can have its own amplitude, so let's kind of give that its own amplitude as well. So this is going to be our output. So let's copy all of that stuff. Let's go copy and paste that into our material function. So the output of this is going to be that. And then we want to provide a couple of inputs. So function input, this is going to replace our amplitude, so we can just do input name, amplitude, add a description, how high, and we can give it a default value of this node. So we'll just give a default value of, say, I don't know, 30 centimeters or 32 centimeters to make it a nice round number, or power of 2 number. So that's going to go into that, and then do the same for our speed and wavelength. So let's just do speed. How fast? And that's going to be our default value. There we go. And our wavelength. So let's do the same for that. Copy and paste the function input. Wavelength. How long, or how far apart the crests are. And don't worry about, well, I want to get quickly onto the Gerstner waves, so don't worry if this is kind of, you feel like this is going slow, because it won't take long for us to kind of get the Gerstner waves going after we've done this stuff. This is kind of just the foundation. And direction, we'll have an input for our direction, because then we can vary that. Yeah, I can talk about the plane in a second. I did that at the very start, but I'll talk about that. So this input is going to be, it doesn't really matter too much about the plane, because this is operating over world position. So your plane can be any resolution, any kind of, position really. It's just going to apply it to the x and y position. So, but with tessellation and stuff, that can affect things. So I'll show that in a second. So this is going to be our input direction, which is going to be, well, we're inputting a 3D and then we're masking it to 2D. So we can just input a 3D vector, should be fine. And then that's going to be 3D input direction. But really we should be inputting 2D, so I don't know. Maybe we should be saying we should input a normalizer one. So that looks like it's okay. Let's do that. And then here we can now just use a material function. So let's go simple sign. And instead of all this stuff, let's just take that out. Let's move it out of the way. But we'll be using our inputs and changing them up. So let's do that. I'm just going to get my... Let's just grab our inputs. I actually don't want space mult. We want our wavelength, our speed, and our amplitude. They're the main ones. Let's just do that. Oh, and our direction. So these are 4 inputs. Let's move them over here and stick them into our material function. So we got amplitude, wavelength, speed, and direction. There we go. So this is our simple sine wave. Now hopefully if we just stick this in here, we're not going to get anything different. We're just going to get what we had. Implementing, no, I'm not implementing the grid, it's just a mesh. We could use the procedural generator if we want, but I mean, I've just got a mesh, so let's have a look at our mesh. So let's just go wireframe. This is the mesh. It's just a simple mesh, and I can't remember. I think I got it from. So I generated it in a third-party application, but I believe if you download the content examples of the ocean example, so let's go to the launcher. I think if you download, where is it? I think it's called Ocean Effects or something. Go to the Learn tab. There we go, and there's this water planes. There we go. What are we doing? What's going on? Back. So water planes. If you download this thing and add it to your project, you'll get a load of grids for low poly grids. I think there's a high poly one in there too. So I could have used one of those. Have I got that in here? I'm not sure. I might have it in here somewhere. Water plane. I think this is it. I think this is the there you go, meshes, ocean water. So this is I think if I make this real time, there we go. So this is what comes in with those content examples. This one. And if you look at the wireframe for that, then yeah, that's quite kind of high res, and that's got world position offset. So it's pretty much the same as what I'm using. You can use that one. So let's just check that this is still doing what we want. Lit. Yeah, so we're using our material function now, and that's just going into our height. So let's just duplicate this. So let's go copy and paste. So now we want to rename these things, because otherwise, if you change these parameters, they're gonna overwrite each other. So let's just go amplitude 2, speed 2, speed _2, and direction _2. There you go. So this is just showing you like how to build something slightly more complex. And we add them together. So I've seen some things on the forums where people add them and then divide them by the number of waves. Here it just says add them, so that's just what I'm doing. I'm just adding them together. So let's just do that. So now, hopefully, if we change our direction, let's just change this to be like that. And I'll change my wavelength and speed slightly. So I'll just go slightly slower and maybe make the wavelength slightly longer. Let's see what we get. There we go. So we're getting something that looks a bit more wave-like. Light source. Let's just move that a bit like that so it's easy to see. And what we're not getting are proper surface normals. So I could make this. So it's adding up now. It's making it a lot higher. So we could just kind of bring down that and bring down that one. So that's kind of why some people kind of divide that by how many waves there are. So we need to develop some surface normals for this, and we need to kind of just explicitly set them rather than the vertex normals. There is a way you can do this with screen space. So you can do this thing where you do ddx and ddy. That's going to take the derivatives, so basically like the rate of change of the actual pixel values, and you can normalize them. I think you can normalize them, and then you do a cross product, and that's one way of setting the normals, I believe. But you can use the actual values of the sine wave to do that for you. And then here you just set world space, so you turn off tangent space, and that's kind of a fake way of generating normals. So that looks a lot better. So now you're getting pretty much proper surface normals. It's a lot more expensive because the ddx and ddy functions are, they're more expensive. But it says normals and tangents. We can do this thing where we, the normal is the rate of change of the position, so the negative rate of change of the position of the height and the positive change. So I've actually forgotten how to do this, so I guess I'll just do this live now. Let's go back to my original material that I had because I've forgotten how to do this. I'll just have a quick peek. And yeah, this is pretty much what most of my shaders look like. So we're doing. I want to go into my thing here. Sorry, I'm just trying to figure out again how to do this. This is going to be a Gerstner wave, basically. Sorry, you have to bear with me while I figure this out. Right, so, okay. For this thing, it's just showing us the kind of the mathematical equation. So it's not really giving us how we calculate it. That's kind of done further on when we get into the Gerstner waves. But because it's the rate of change, technically it is going to be the derivatives. That's what it means. So if you take the derivatives of sine and cos of our simple sine wave, then basically you're going to get the normals out of there. So I've not, yeah, it should be pretty simple to implement, but for some reason I'm getting a bit of a brain block here, so. Because you want to get the rate of change of that with that, which will give you the normals in that direction. And that's effectively what the cross product is doing. It's just doing it in screen space, whereas you can actually do it just with the sine and cosine functions here. Anyway, I'll just get on with the Gerstner waves things, because then, I mean, I know how to do that with the with this. So yeah, I guess I'll just do that. So anyway, we're gonna do Gerstner waves now. Woo! So let's do it. Let's go to our paper. So we've already kind of done basic adding up with sine waves. Now Gerstner waves, this stuff here goes over how you can create like a little bit of a peak. So when you're doing simple sine waves, you can, if you raise everything, so it's positive. So if you basically add 1 to everything, because sine's going to go between -1 and 1 basically. If you add 1 and then divide by 2, you're basically going to shift it to 0 and 1. And then when you multiply by 2 on the amplitude, it brings it back up. It kind of gains everything. But then if you raise this to this kind of k parameter, it's just a user parameter. What it does is it kind of this power function kind of, instead of getting this black one, you get this orange one, where if you raise it to 2.5, you get more of a peak. So I could show that here. I've not done that yet, so I'm kind of improvising. So I've got the output of our sine wave. I'll have to do it inside the material function. So if I go into here, yeah, I can do it here because it's before the amplitude. So what we want to do is, I'll briefly do this because this will give us something a bit more interesting. And if you want to just kind of get some really simple ways, you could just do this. So let's add 1 and divide by 2. So add 1, and then we're going to divide by 2. Because the add 1 needs to be done to the whole of everything previously. So divide by 2, so that's going to go into there. Now that needs to get raised to the power. So this whole thing, which is a +1 divided by 2, that needs to get raised to a power, and then you multiply by the amplitude. So we're going to do power function, and then we'll do base, and then the exponent. So the exponent is our parameter. Base is what we're going to be raising to that power. So let's just do what they say, the 2.5. 2.5. Make that a parameter, and we'll call this peak, and that's going to go to here, and then this needs to be multiplied by 2 to kind of satisfy that thing. So we're just going to go 2, hard code it. I should do it the other way around. Just do that. 2. If you want to make it explicit, then you can just do this. Makes it easier to see at a glance. Like if you're out here, it makes it easier to see what you're doing. So do that. I can make this a function input, this peak thing. So let's make this a input, and we'll call this peak, and say raise power to cause peak. So let's save this, and this is now erroring because it needs that peak. So I'll just copy this and paste it here, and we can now input that as a peak. This one will be error out to because it's the same, so this needs a peak, and I'll just do it to both of them. Use the same parameter because we can control that globally. So now what I want to see is a peak. There we go. So this now it's going to go like, if you have it at 1, it's going to be smooth, no change, because if you're raising it to the power 1, you're just going to get 1 out. And then if we go higher, that's going to be our peak. So you can see that what we're doing there when we raise it to 2.5 is that similar to what we had with this kind of curve thing here. So we're just creating a peak. So that might be enough to give you whatever you want. Let's make this a bit more interesting to look at, because for the moment it's a bit boring. So I'm just going to bring in this sea texture, because why not? So let's just apply that to our grid. This is going to use the UVs of the grid, so this is going to stretch across the whole grid now. There you go. So that makes it really easy to see what's happening. So yeah, so you can really see now why sine waves might not be the best option, is because it's literally just going up and down, and this texture is really obvious what's happening. I mean, if you're doing something stylistic and you're not using like a proper texture, then you might want, if you're doing toon shading or something that's kind of not as obvious to this, then you know, you might want to, it might be okay for you. Or if you're doing it at a distance. Let's change this direction again. Let's go a bit more. So you don't need B because it's being masked out anyway. So we're going between 0 and 1. Let's make this amplitude higher to make it obvious. There we go. And make this one lower. There we go. So at a glance, this might be what you want. And you can kind of see there when I'm scaling up the grid, then it's not changing the shape of the waves, but the texture is kind of changing up. So you might want some extra control for the coordinates. So I just normally have a texture coordinate going into a multiply with a constant, and I just normally make this a parameter and call it UV mult, UV mult, and this will be some multiplier, and that just goes into the UVs, and that's just going to give us like a really basic multiply control. So for 8, there you go. But then texture repetition really becomes an issue. So I want to look into using texture bombing to kind of vary up these foam textures. But you can kind of see already we're getting something that kind of looks acceptable. You can increase that peak even more. There you go. So yeah, one's completely smooth. So you're getting completely smooth sine waves, and then adding in that peak parameter. I mean, it gets you kind of a lot of the way there. But we're going to introduce the Gerstner wave behavior now, which is going to just pretty much add in some cool swelling effects. So the paper then goes on a little bit about circular waves. So instead of doing like these 2 input waves here, which vary in direction, you can use like an origin point, and then you get these kind of concentric waves, which will be good for like ponds and stuff and that kind of thing. But we're here to talk about Gerstner waves. So this is the Gerstner wave equation. And again, you can read this as the position of the vertice at the world position x, y at time t is equal to this. And it looks a bit weird, but basically it just means this is your x coordinate, this is your y coordinate, and this is your z coordinate. And again, we've got this summation thing here, which is like the summing up of all of the different waves. So breaking it down, we've got again, we've got a dot product with position plus our phase times time. So we've already got that pretty much, where W is our speed kind of input. The only thing that's changing here is instead of sine, it's doing cos. Not really sure why. I think it's just because it's offsetting it, and then sine is going to be the height. Okay, so yeah, backtracking just a second. This is what we had before. This is the exactly the same thing as our sine wave. So the z is the height, and then x and y are going to be our side-to-side movement. So the swelling. So it's going to, these vertices are going to kind of go left and right depending on how close to the peak they are. So here we've got the same actual thing. We've got this, whatever's going into the input is the same. So the cosine, that's how we're going to get that side-to-side movement, is because it's doing kind of like the offset from sine. So as sine goes up and down, 0 to 1, cosine is going to do like the kind of, if you overlay sine with cosine, let me just try and find an image. Here we go. So if I just do this, you can kind of see, if you overlay sine and cosine, you can kind of see sine's doing this thing, and cosine's going to be doing the kind of the offset thing, but exactly the same. So as sine's going up and down, this thing's going to be going side to side. So that's why we use cosine here. And then we're kind of doing this thing where we take the x component and multiply it against this amplitude and steepness parameter. So we'll do this step by step, just the same as we did this. So we got cosine going side to side, and then we're multiplying that by this kind of like, this is your direction in x for your wind direction. So that's going to affect our swelling according to the wind, and then we've got this q parameter, which is the steepness, which is defined by q equals, so our q at I for this wave equals our input parameter q. So it's really annoying that they've kind of they've named this thing qi, whereas q is like what you're actually inputting. So this is your result of you inputting q. So it's not really made clear that, and then that's what you multiply against. So you have, and then this num waves, it doesn't say what this num waves is, but I've kind of figured out the hard way that is the number of waves that you're adding up. So before we added these sine waves together, we had 2 of them. That's kind of what that is. And then again, I've figured out that there's like an extra parameter that we put in, which actually isn't in this paper at all, but I had to put it in to kind of correct the values. So let's just go in and put this in. So we've got our height, and that's going to go, that is our that's our thing going into z. So let's do the x and y. Now I can take the simple sine wave. I'm just going to duplicate it, because let's duplicate it. Where is it? Simple sine. I'm just going to say asset actions, edit. I thought there was a there we go, duplicate. So we're going to duplicate this, and we're going to call this Gerstner. Let's just do simple function. Simple function. There we go. So now let's edit this. So we're starting off basically where we left off, and we've got our height. So we're going to want to get our actual make 3 vector thing here. This is what we're going to output now. So we'll just copy this into our thing here, and we're going to output the final value. So let's just stick that in right now. And let's create our x and y. So let's do our, let's change this to cosine first. So actually, this whole input thing here, so this w times direction thing, that's just, before it was written as d dotted with x and y times w, but this is just bringing the w to the start. So d times, that was w times dp, that's this thing. So we can kind of rename this to be like inner function. Let's just kind of put that in brackets so we know what it is. Inner function, and we're going to use this as our into cosine. So here it's going into sine, and yeah, everything. So this thing here actually inner function. There we go. Actually no, that's W times dp, and then just keep that as it is, and then this is our inner function. There we go. So this is like the result of everything inside here, which is the same for all three. The only difference now is we have a cosine, so let's do a cosine, and then that's going to go into our inner function. Let me just move this peak out of the way. Actually, for this thing, we're going to get rid of the peak. So let's, sorry, 1 second, I just want to see what we're doing with that amplitude. So amplitude. So the A is used the same for all three. And then for that, it's multiplied by Q. Okay, so anyway, let's do amplitude. So yeah, we can multiply by sine. Yeah, so that's what that's doing. And we'll move peak out of the way. So we'll try and keep this clear. So let's move it out of the way. We might use it later on, who knows. So we've got our sine and our cosine. So the sine and the cosine are the same for both, so we can keep that. We can use the same result, which is this thing here. That's the result of putting the inner function into the cosine, which we've done with the nodes. And then we're going to multiply that by the x component of the direction. So let's get our direction, our wind direction, and we want just the x component. So let's do a mask, component mask, and then we're going to get bring that over here. Now let's do that, and we can just comment this, and we can say x component of wind direction, and that again here, wind direction, and then that's our cosine, and then we multiply those two together. So that is now this whole thing times that, and then we need A times Q. So we've got A, so let's just multiply by A. Hold M, get a multiply, and we've got A. So let's just do A. We want our input there, so we do A. And the last thing we need is this Q parameter. So what is Q? So Q equals input Q times WA times num waves. So we need this num waves thing as well. So, but we've already got W and A. That's really strange because we've already got A here. So we're having Q divided by, I think that's what it's doing. It's doing some kind of dividing by this value and then re-multiplying it. So you're getting some kind of non-linear thing based on the frequency. Yeah, I can't really explain that very well, so sorry about that. But what it does, yeah, it kind of, you'll see what happens when we kind of when we see the things moving. So let's do W. Let's get this Q value. So input num waves. Let's create one for num waves. Let's go. Num waves is going to be a parameter. Num waves, and this is going to be, for now it's just one, and then we want this to be a function input. So just get one of these. So num waves. And this is going to be how many waves we have summed. And then we also have Q, so let's get a different, oops, copy that, call this Q, and this is going to be steepness. So Q, this is going to be a value between 0 and 1. So Q steepness, and again this is the kind of our new peak. This is going to be how we're getting our peak with this one. So what we want to do now is have Q equals Q divided by WA times num waves. Now I'm pretty sure this is wrong, how they've done it in the paper. So WA times num waves. So we've got W W times A times num waves. So here we go. So W, which is this thing, wavelength times amplitude. Make sure we're getting the right input. So W. Now we want W. Yeah, we definitely want W, and that's the input. It's W times A times num waves. So it's W times A times num waves. There we go. So we've got this is W times A times num waves. W times A times num waves. And then what we do is we say Q divided by that. So we're doing Q divided by that. So this now is our peak. This is our QI. Just again, I think it's stupid the way they've done that in the equation. I would have given it a symbol or something. Cool, so we've got that. So we just multiply it against that amplitude now, and against our actual direction. So what our amplitude? So that's this thing times that thing. So this is the A. This thing here is the result of everything else. So that's all of this. So all of this. Now we just need to multiply by Q. So we need to multiply by Q. There we go. So now that's our X, like that. And now we need the Y component. So this might need a bit of rearranging here to make it a bit easier, because then we can reuse QA times cosine, and then we just need, at the last stage, we can use the same result to do X and Y. So imagine these are at the beginning, and we're going to do, here's our cosine times, it's cosine times QA. So let's take out that, and let's get our X component and do that, and bring these back. Sorry, it's getting a little bit confusing, so we're going to put that in here. So this QI thing, we want that with the amplitude. So this is the result of, let's just disconnect this and do it a bit cleanly. So we have, this is QA, here we go. So this, there we go. So this is QA. That's what this thing is here, QA, and then we'll multiply that thing by cosine. So this is everything now apart from this X component thing, which is what we got up here. So we've got the X component, and now this is everything else. So let's just call that everything else. Else, because now we can reuse this everything else thing. Let's multiply the X with that, and now let's just see what we get now. Let's see what we get. Let's do that. We just output 0 for the Y component, because this is an offset. So let's do what position offset. So now we're going to bring in our Gerstner function, and we're going to input wavelength, amplitude. We need a peak value, so let's just steal the Q and have it outside, so we can just put it in. Num waves, we haven't got a num wave, so we'll do the same thing for that as well. Num waves. I'll move these out of the way so I can disconnect them. Yeah, there's a beautiful sine wave. So hopefully we're going to see some nice side-to-side movement now. So let's go input direction and peak, which is, we don't need peak anymore. We're not using it because it's going to complain. But I'll keep it around. I'll just plug it in just so we don't get an error. Peak and speed. Speed. So all of the kind of traveling waves thing should be the same. And now we don't need to combine it because we're doing it internally here in the Gerstner wave. So let's apply that and see what we get. Well, it's not broken, so that's quite reassuring. Oh, there we go. So we got something. It looks broken, but I'm pretty sure I know why. So there's our peak value. So okay, so 0 peak. So you can kind of see this is a single wave, and without peak on, then we're getting just what we had before, up and down. Now as we start to introduce this, you can see how we're getting this swelling side to side. And remember, this is just in X. So if we're looking in our viewport like that, we're just getting the movement in X, and we want it to happen in Y as well. So forgetting the fact that this Q value is a bit weird, and we're setting it to 0.1, and that if we go too high, you get this kind of like weird, horrible peak breaking thing. We'll fix that in a second, because that's what I was mentioning before about the paper being slightly wrong. But let's go back into our Gerstner function and do the same for Y. So all we need to do now is, because we did this everything else, which I'm calling it everything else, is because I mean everything apart from you know, this thing here. And now we can use that same result for Y. So let's get the Y component, and we can just duplicate this now and hook it back up to the input direction. So this thing over here we're using for our dot product, and that's all going into the Z, but we're doing the Y here, so we can ignore that. So now we need to mask based on that. Comment, and we can say Y component of wind direction. And when we say wind direction, this is the direction the wave's traveling in because of the wind. So it's not real, like, you know, real wind, but effectively that's what the reason the wave's traveling is because of wind. So let's multiply this everything else thing by the Y component, and now that can be our Y. So I think this is going to do what we want. Let's have a look, see what's going on. Looking a bit broken, but let's have a look why. Let's go back to our master material and have a look at our Q parameter. There we go. So having to bring that down, and now you can see what the cosine is doing. Is it's if I go into wireframe, actually no, wireframe you can't really see it because it doesn't do well position offset in wireframe. If I plug this into tessellation though, you see the wireframe. So let's do that. Let's disconnect this, turn on tessellation, and unfortunately this only works on Windows, I think, because of Epic not putting it in on Mac. Hopefully with Metal and 413 this might work, but as far as I know it doesn't work yet. So this is going to be our world position offset. Instead of world position offset, we're actually displacing the surface now. So now if we look in the wireframe, yeah, we're getting that cool Gerstner wave. And you can also see the tessellation is going to be cool when we start adding in more waves at high res. So you're getting this cool swelling movement. So the height is being done with that Z thing, and then the X and Y are kind of, that's what the cosine is doing, is it's making it go based on that frequency and that speed, then it's making it go left and right. So hopefully that's all making sense to you. Let me know in the chat if like that is weird and not making sense to you. But let's fix this Q parameter because that's bugging me. Let's go to our thing. Now, it doesn't say what that really means. So I've actually figured out that we had to actually divide that value by 2 pi. Let's go to our, I've got my previous one over here. So this is my previous Gerstner wave thing which I made. And this is pretty much what I'm showing you as well. Like this is what I just remade. I'm doing, so instead of everything else, I called it cos of all that. And there's the Z, which is the height thing, and here we've got the X and Y multiplied by the X component of the wind, QA, all that kind of stuff. So let's go to our, here we go, extra not in paper, num waves times 2 pi. So num waves gets multiplied by this 2 pi. So let's do that. Let's get our Gerstner wave, simple func, and up here in num waves we multiply it by 2 pi. So let's do, actually I believe it's over here already, so let's just get 2 pi and bring it up over here. Pi, and now let's go multiply, or my favorite, just hold M and place it. So let's go multiply by 2 pi, and let's do that. And now fingers crossed this really fixes it, because I'm pretty sure it should do. It's okay, so it's looking a lot smoother now. And if we go back to our main material, now go between 0 and 1. Now, so we're getting a full peak at 1. So this is where it's at its sharpest, and you can kind of see like that. So you're going to get a nice sharp peak. If you get over this value, then what you're going to get is it breaking. So if I go 1.5, then that's the point where it starts to do this kind of weird loop over itself like that. So this is kind of related to physical waves. And this is the point that waves break. And when they're coming in on the beach, they reach the kind of tipping point and they break and they kind of smash in physically. But because we're just dealing with a flat plane here, it kind of just loops in on itself. So keeping this to a value between 0 and 1 is what keeps it from breaking. So 1 is a full sharp peak, which might be a bit extreme. I found that having it up around 0.6 or 0.65, 0.5 kind of gives you things that aren't too crazy. And it also depends on like what scale your wave is. Like you might want your smaller scale waves to have sharp peaks, and then I don't know, larger ones to have smoother peaks. But it's all kind of artistic at this point. So here is where we can start summing these things up. So if I get rid of this simple sine wave, and then duplicate this, now I can use the inputs for another direction. So let's go to wavelength 2, amplitude 2, and combining these Gerstner waves is where it really starts to look pretty cool. Go to input direction, speed. One thing that the paper recommends is that you kind of duplicate these things and then use the same inputs, but kind of do things like divide by 2, multiply by 2, to kind of get like ratios of frequencies and strengths and stuff, and that can give you interesting results. And that's what I was kind of showing earlier on with my final thing. Num waves. So that now is going to change depending on when we add these things together. So we do our Q value. steepness and peak. We don't need peak, but it just kind of keeps it happy, not airing out. Actually, let me take out peak because we don't need that. Let me just delete this input function. Sorry, no, delete that one, delete that, yes, apply. So now we don't need that peak, and that should be it. So now we can add these together. Let's add them. And let's see what we get. There we go. So we're getting two directions now superimposed on top of each other. Let's play a bit with the directions and stuff. So this is kind of, you can kind of see now the one's going that direction. Let's just do that. Maybe the amplitude is a bit high. Let's just do. Let's make one go this way and that one go that way. So, oh, they're both going in the same direction. That's not useful. Let's do that. There we go. So now they're going. This is where you start to kind of see cool behaviors when you kind of have them in kind of crisscrossing angles. So changing the speed is going to make a difference here. So let's make these both like 120 or something. Let's make the speed the same for both, just to make it easier to change these settings. What you can do is you can do two waves at the same frequency and same wavelength, but change the angle. And then, okay, this is where I'm going to dive in now and show you how you can build more complex arrangements. So I'm just going to keep this here. Let's duplicate these two things and move them down. And I'm also going to duplicate my inputs and rename them. So here's going to be my second set of actually the wavelength and the speed. I'm going to derive them and the amplitude. Let's just change the direction. So everything is going to be based off of these main parameters. So let's say that the wavelength for the first two is the same. Let's delete that, and the amplitude is going to be the same. So let's do that. The only thing that's changing is the speed. So we've got the same speed, same amplitude, same wavelength. The only thing that's changing between these two is the direction. So we can do the same for this, but then we're going to divide these all by 2. So wavelength, we're going to divide it by 2 because that's going to make it shorter. So at the moment it's 4 meters. Let's just do that, and I'll show you this. This is a 4 meter wavelength. And I can make it go faster if I want. So 4 meters, but it's traveling at 2 meters per second. And that Q is quite high, so I can do that. So here's the sine waves, you can see that. And let's 0 is going to be sine, so just up and down. There you go, that's just up and down. Simple sine waves, same as we had before. 0.5 gives us the swelling and the peak value. Now I think there's a way of arranging the function so that the amplitude controls the swelling as well. Maybe that's what got me wrong with the rearranging of things, but for me it kind of makes it easier to just set up the nodes that way. But okay, let's get this set up. So I'm going to get my input parameters. Some amplitude is going to be multiplied by 0.5. So I'm going to halve my frequency. No, sorry, halve my wavelength. So the next level of waves are going to be closer together, basically. And we could change this input parameter after as well to make it not exactly half. If you make it exactly half, you'll look fake and horrible. I mean, it looks fake and horrible anyway, but you know, we can minimize that. So we're going to halve this distance, and we're going to halve the strength that we're adding as well. Because if you add the same, it's going to pile up and up and up and up. So and we'll also halve the speed that they're traveling at. So we're going to have 3 multiplies, all multiplied by 0.5. So let's get our wavelength, which is that. Amplitude which is that, and our speed. So this is going to be the input to our next couple of waves. So this is the, oh, that's annoying. This is the wavelength, so that's going to go to wavelength. This is our amplitude, it's going to go to our amplitude. Let's do it to both of them. Wavelength, there we go. And this is our speed. Speed. So num waves is going to be the same for everything. Oops. Ugh. Num waves is going to be input into here. And this is where we're going to have to change num waves globally, because num waves is going to be it's going to be 2 now, because we're adding up 2 waves. Actually, it's going to be 4. So technically, what we're seeing right now should be 2. There we go. So that kind of helps control that side-to-side swell. And then you can go higher with Q. There we go. So that's kind of why we have num waves, is it controls the swelling depending on how many waves we have. Because if we add up all the waves, then they're going to be swelling. That swelling is going to add up too much. And this num waves kind of normalizes everything and brings back everything within the same range. So Q steepness, that's going to be a global thing. They're all going to have the same Q. You could have different Qs for different levels of waves. But now is where we're going to get into different directions. So this is going to be direction 3. That's going to go to there. Actually, let's just do that one. And then we'll duplicate this and do direction 4. So this is going to be 2 extra directions. So let's make this go that direction. Let's say, actually, and these can go in negative direction as well, but you have to multiply by them by 0, 1. So by -1. That's really annoying. Let's multiply by a vector. So if we hold 2, then actually we need to hold. Let's just multiply by 0, 1. By -1, sorry. Let's make it go in the opposite direction. So we've got this. So if we multiply by -1, it will go -7, -0.4. So yeah, it doesn't really matter. This can go into there. I'm trying to figure out a way to kind of make this more visual, so I can rotate something in the viewport and pass it through as a parameter to the shader. But for now, I'm just doing it with these random directions. Yeah, let's do that. And then we just add them together. Add. And then we add them all together like that. Let's go add. And then they'll finally go into there. So let's hit that and we'll see what we get. Hopefully it's quite interesting. Whoa, crazy. Why is it looking like that? That's a bit weird. Maybe the amplitude is just too high. I need to bring the whole thing down. Okay, so change our num waves to 4. There we go. So that's why it was looking pretty crazy. So that's about right. Let's make our amplitude higher. Let's make our Q higher to kind of see what we're getting. I think our directions are playing against us. Let's change the direction. And this one, let's just do that. There you go. So when we change the directions, that kind of helps things. And yeah, we've got some in B, but to be honest, it doesn't really matter. A lot of this is going to be playing around with different values to kind of see what you get, because you want them to all be playing against each other. So this is only 4 values, and it might be traveling a bit fast actually. So this is like that. 60. Oops. Yeah, so kind of getting somewhere that's kind of where I want to be. So this amplitude, really I want it to be controlling that Q parameter. So I might need to do a bit of refactoring, so you can kind of see when we've got nothing, it's just going up and down, and then 1 side to side. I'd also like, so when we've got this Q parameter at 0, you see it's going side to side. And I don't want to see that really, so they should be linked. Now, going back to the paper, Q times A, yeah, I mean really, I don't know why they're not affecting each other, but yeah, I might need to just rearrange this a bit. So Q times A, let's go to our Gerstner wave thing. So QA. Yeah, I'm gonna leave it as it is because it's I mean, I've got it to a state where it's working. I think I might come back to this in a couple of days and figure out why it's doing that, because that looks, obviously we want the amplitude to melt this down as well. It's probably a simple matter of, you know, rearranging those things. Just have a quick little think. So X component, so that's that thing times cosine times QA. So if we have amplitude down, surely that multiplies that steepness down. And then it's going into that. So weird. Maybe that should be last. So maybe, so this stuff makes it a bit hard to see. Let's do that. So this QA thing, if that's last, so instead of going from, so we've got the X component and the cosine, okay, so let's disconnect that. This is everything else. And then that's going to be like that. Okay, so we're going to have, yeah, so everything else multiplied by the X component. So that's going to be everything else Okay, so yeah, everything else, which is this, multiplied by the x component, and then everything else multiplied by the y component, and then we're going to need two of these, so QA. So I'm guessing this is going to be a bit slow, it's got that extra multiplier there, basically. I don't know, I'm kind of making this up. It's QA. So we need to multiply here. So we need to multiply QA by this thing. I don't even know if this is going to be any different, but gotta try. So we have QA. That broke. Actually, no, we don't need two of those. We need. We can use the same thing, but what we do is go into here, use QA times that, and now this is our Y thing. So let's see what that does. So it's definitely not breaking. But still going side to side, and let's do 0, 0, 1. Yeah, still going side to side. So I'm really not sure what's going on with this thing. Because it's being multiplied by. Okay, so let's. Yeah, that should be multiplying to 0. So if amplitude is 0, it should be multiplying to 0 here. It's really weird. Why have we got? So that 2 pi thing is going into this. That's for Z. So QY. Let me check my original Gerstner wave. No, because that was happening there as well. I remember that being the same mild one. So amplitude is 0. That should surely multiply this to 0, which multiplies that to 0, which means we don't get any offset. But we are getting offset. I'm really confused. I don't understand. I'm probably doing something really stupid. Make sure I've got the right inputs here. So amplitude. I can't set it to 0 because it's that would be a divide by 0 error. So amplitude. Yep, definitely connects to amplitude there and there. And on that one. Right, I'm gonna have to sleep on this because I'm really not sure. Yeah, definitely should be going to 0 here. Oh well. I mean, at least it is pretty much doing what it should. Let's go back to our lit. So as long as we put in, you know, reasonable values, we're getting something that looks like water. And yeah, so that's a 0 gives that. Cool, so I might just kind of leave it here. Yeah. I mean, that's pretty much what I had before anyway, so I've kind of recreated what I had. So what I might do is just wrap this up and put this online somewhere so you guys can grab it and play with it. Let me save this level. Save as, there we go. Let's call this Gerstner test. And I'll quickly go back to the original scene I had at the beginning with all the, I had 8 waves added together. So if I go to open level, ocean, save everything. So this is what I had before. So I've added, the only thing that's really different is I've got 8 levels of Gerstner wave. So let's add a bit of my material. And I'll quickly have a look at this. So I've got my Gerstner wave thing, which is pretty much just what I've just done now. I've got my input parameters. I've got 2 low frequency ones, 2 kind of normal size ones, then double the frequency and then double the frequency again. And at each stage I've got this kind of ratio, so frequency ratios of like here's 4 or 4.2 whatever, and then here's 2.1 or 2. I don't know, so it's 2.1. Here's my main wavelength, which everything's based off, so that's 6 meters, 600 centimeters, and then here I've got a frequency of let's say 0.6, and then depending on those values you get like different behaviors. So if I change that low frequency one then to say 0.4, you get a kind of overall lower swell. There we go, 0.1. That's like a really that's like the multiplier on the main. So 6 meters, that is kind of making it a lot lower frequency. It's a multiplier on the wavelength. So it's like 1 divided by that. So it's like kind of like the inverse frequency. So then, yeah, you can control that. And then in the higher level ones, you get kind of the more detailed level. So if I change my ratios down here, so this is my main wavelength here. I can set that to be like 8 meters or 12 meters or whatever. You can kind of see everything else adjusts around it. So I'll kind of set this to be somewhere in the middle like that, and then these ones I just multiply on top of that. So I can go to 3, and then you'll get kind of like the waves that you'll see. The detail waves will be less strong, but kind of more subtle ones. And then again, another more detailed one. So I could have ones that are kind of quite close together, and they'll play against each other, or going to have like a really high detail, and then you'll get like micro detail. But, and you can kind of see it shifting a little bit. And the more subtle it is, the better, really. And then I'm playing with my amplitude. So yeah, I really want to go and you can kind of see the sub levels if I really boost it, but if I do that, boost it quite high, and then I can play with my steepness to kind of get more peaks. So yeah, I think I'll finish the stream soon. If there's any final questions from you guys, you can stick them in the chat. I'll probably post this on the forum, and you guys can just grab it from there. I'll probably stick it in the where shall I stick it? I'll post a link to it. I don't know how I'll get it up yet. Maybe it'll be like a Dropbox thing. Let's go to the forums. I'll probably stick it in the community content tools and tutorials section. I'll stick that here somewhere. So yeah, it'd be quite interesting to kind of see if anyone else can come up with a better system. But I kind of quite like how this is looking. You can see my texture here. I'll quickly show you guys how I made that texture. I basically imported a free texture that I got online, and so let's open one of those up. Let's go to desktop, documents, what was it, downloads. So let's say seawater foam. So this was a non-square texture, so what I did is simply just get my canvas size, and I kind of made my canvas size, let's just make this one 2K because that's fine. So that will kind of crop things if it needs to, but the layer's still there. I actually just cropped it, but that's fine. So we want to make this repeatable, and all you can do, you can just go to filter, offset, and you can offset like half the amount in each direction. So that gives you this. And then I use the healing brush to basically just do that down the middle, and that will kind of use content aware fill to do a pretty good job of fixing these seams. Just give that a second, and then see, it's a pretty good job, and then do the same that way. Pretty cool, and you might want to go through and do some kind of like that to kind of break up the patterns so you don't get these kind of things like that, but it does a really good job of filling in the seams. There we go. And then the last thing is you can offset it back, so back to, oops, sorry, cancel, filter, other, offset. You do it back, it should keep the same settings as last time, and then you'll have a couple of areas where it's kind of a bit like dodgy, so you might just want to fix those up. Just there, without having to go right to the edge. Just get there. You'll see some weirdness sometimes, but as long as you're quite careful, you can zoom in if you want. Kind of fix these up. So once you're kind of happy with that, you can save it up. And I'll save it as, I'll just save it as a PSD. And I'll just save this in my game assets folder, water textures. Let's just call this C-Foam2. And I'll just save it as a PSD because Unreal can import PSDs. So let's do that. And you can kind of see before I've got these kind of lines where I missed those edges. So now if I import those ones, let me just grab the file, C-Foam2, let me just drag that in. So let's go to my master ocean. There we go. And I'll just swap out that texture for my new one. So C-Foam2. So this is the one I've just brought in, imported. There we go. So that should hopefully fix all of the seam issues and stuff. So what I want to do next is experiment with blending some of these foam textures so that the foam kind of goes in and out and get more at the peaks and that kind of thing. So yeah, cool. I'll just finish this up now. Thanks for watching, guys. All 5 of you. Wow. I'm famous. Yeah, look out on the forum. I'll actually, if there's a way for me to do that now, it'd be nice to kind of just post that out there. Let me just log into Dropbox to see if there's a way to do this. Right, so just pasting a link in the chat. Hopefully that should be able to be downloaded by everyone, and that is what we've done today. So it's the easiest thing was to package the simpler one, because the other one has a lot more kind of textures and material functions in. But pretty much this is the one I've got, which has got 8 different levels, and I've got these kind of controls. So I've got like a master wavelength of 800 centimeters. So if you stick that as your main one, 800, then and then go kind of twice higher than, you know, twice lower, and then even again like another twice higher above that one, then you should get something really similar. So I've got speed of 28, so speed of 28. And wavelength, amplitude. So the amplitude is 2.6, steepness 1. Full steepness. Also, you can play with your parameters. Without that lower frequency, you kind of see less variation, but it doesn't look too much different to this one. I mean, you can see the lower frequency one there. But with a bit of tweaking, you can kind of make it look cool. Make it a bit faster. Yeah, so feel free to download it, and yeah, I'm going to stop the stream now. So if any of you want to find me on Twitter, you can go to, you can find me, oh shit. There we go, this is me. There's my lovely mug, at Daniel Elliott 3D. So this is me, at Daniel Elliott 3D. Yeah, feel free to follow me. If you want to find my YouTube channel, then I'll just take you there. 1 second. Go to YouTube. Then I am this guy, so DokiPen Tech. If you just go to DokiPen Tech, then you'll find quite a few videos on things like that. And feel free to subscribe and ask for any kind of requests on things you want to see. I'm going to try and go away and come back with fixes for that steepness, which was bugging me. The last thing you might want to do is multiply this up so you get more detail out of it on the texture. There you go. Even that looks a lot better, just having more detail on your textures. The other thing is that the smaller this thing is, the more detail you're going to get in your tessellation. So if you look here in the wireframe, this is going to kind of go up if it can. Like, if this is too high, it won't be able to tessellate that high. There you go. So this is like, you know, it's tessellating it, but it can't go that high. It should be able to though. I mean, I need to look into tessellation more really. But yeah, adding out multiple levels here will get you quite far. That far even. You can kind of see, like, if you've got more waves added up, you just get a lot more interesting kind of swirls and sub swirls and that kind of thing. It just helps break things up. Anyway, gotta go now. So cheers for watching, guys. I'll probably upload this to YouTube as well, so look out for that if you want to watch it back. Cheers.